Yesterday we were talking about the spectrum of FM signals, that how do we try to find, or why is it important for us to know the spectrum of FM signals? So one, why is important for us of 2, how do we this? So my question marks are bad. Yes. So is point 1 clear? Why do we need the spectrum of FM signal? Is that clear? Because only then we should move to point 2.
So is it because we are trying to?
No, my question is that, is it clear to you? If it is not clear, then I'll explain it again.
So could you
Can you
explain it
summarize it?
again?
Yes,
I'm
that's the easy approach. So let's first answer the why. Yes. So to answer this why, we have uh, so when we talked about AM, or when we are talking about communication, talking about sending information from, so this F is really bad. Let's erase this. From one point to another. Right? This is what we do when we think about communication. That when we are doing communication, we are basically sending information from one point to another. But as we know, so there is one golden principle that governs all engineering practices. So all branches of engineering work on one simple principle. Can anyone guess that?
say efficiency.
Efficiency is something else, something even uh, more fundamental than efficiency. Some principle, some law of nature that governs all engineering practices.
Conservation of energy.
Conservation of energy is not exactly conservation of energy, but I should say rather a philosophical principle. So the principle that I'm talking about
So
is
cost.
huh?
Cost.
Cost, yes. Or stating that simply or more colloquially, I would write that the principle that we are working on is that there are no free lunches. There are no free lunches. So since there are no free lunches and we are sending information from one point to another, it will have some cost, right? This information will have some cost, and we have identified that for communications there are two types of cost involved, or two costs involved. One, bandwidth. Two, power. Suppose you are having a shouting competition with your sibling, or your sibling tries to read your WhatsApp chat with your crush, and you want to let the entire locality know that I am not happy with this guy. So what you do is you consume a lot of power. You shouting requires a lot of energy, so you consume a lot of power, and you don't allow anyone around you to communicate on the baseband. You speak so loud, so you consume a lot of bandwidth, but you get the message across that you shouldn't you shouldn't see my phone, or you shouldn't use my fingerprints to unlock my phone while I'm sleeping. Yeah. So anyway, so this cost. So, and as good engineers, or as engineers actually, I don't know why is this. As engineers, we talk about efficiency, which is a polite name or value for money. Yeah, there are more impolite names of value for money. I won't state them. I would leave them those to your imagination. But I say that the efficiency is mainly a polite form of value for money. That I'm spending some bandwidth, I'm spending some power. What do I get in return? So obviously, when we are talking about a modulation scheme, should know about how good, bad is its performance. Right. So we are talking about the modulation scheme. So we should have an idea that okay, this is this good or this is this bad. So you might remember that when we talked about AM some time back, we said that AM is particularly inefficient in terms of power, and it is inefficient in terms of bandwidth. Similarly, we so we said that because we could simply analyze the power in FM, power in AM, that AM, simple AM, you allocate at least 66% of the power to the carrier, and we had ways of, or we had rather empirical ways of getting around that allocation of 66% power to the carrier. Similarly, we said that we are actually using since we could analyze the signal, we said that we are actually transmitting the same message over the bandwidth twice. So there should be some way of not doing that, or using the bandwidth more efficiently, and we came up with the single sideband modulation, as well as we came up with the quadratic amplitude multiplexing. And because of these signal analysis, we were able to figure out the Costa's receiver. So that envelope detector was simple, that was based on the envelope, but Costa's receiver and all the fancy things we were able to do with AM, because we could analyze the signal. So, and as an important part of the analysis, we should know the first step in analysis of any signal. So now the first step, the any signal, or rather any deterministic signal, since till now, so deterministic signal is the analysis of its spectrum. So side question, do you know the difference between deterministic and random signals? Do you know the difference between deterministic and random signals?
Yes, sir.
Yeah, Adit.
Yes, sir, we do. So deterministic signals are basically signals for which you can tell, for any time instant you can tell them what their exact value would be. But for
Okay.
random signals, they have, you know, the distribution of how the values will look in the long term, but you can't really tell what the
No, we'll
next
cover random signals in detail.
yeah.
Random processes, since you guys told me that the your random processes portion was a victim of this COVID pandemic. So we'll cover random processes in detail. But you have an idea of deterministic and random signals, that's good. So, and till now you might have noticed that we are only talking about modulating these carriers with deterministic signals, right? So one thing is, we practically we do not want to modulate the carrier with deterministic signals. Can anyone tell me why is that? Yeah, Shubhashish.
Sir, you are telling that we do not modulate it using deterministic signals.
I'm asking you why we uh, practically, why is it nonsensical to modulate anything with a deterministic signal? For theoretical analysis, it is easy, it is good, but practically, why is it a bad idea?
Sir, because anyways there's going to be noise in the channel. So I think, I mean,
Something
even if
again more basic than that. All those who cannot see the screen, like Abdul's post. Okay, I'll unshare and reshare.
sir, creating this deterministic signals is tough, difficult.
Absolutely not. You have done that. You have done a lab. You have done any lab with AC generation where you had a signal generator.
Yes, sir, instrumentation labs.
Yes. So why is the yeah? So someone please speak. It seems that yeah,
Sir,
Subhash, it's okay. It's okay. Somehow my connection dropped in one place. Yeah. So uh, no. So deterministic. There's so say uh, in the or as opposing deterministic signals, I see that quite a few, only a few people are interested in attending the class. But would you guys be interested? Means those who are still interested. I'm just talking about them. Would you guys still be interested in attending these these lectures, or for that matter, any online or offline lectures, if you knew exactly what I was going to say? Would you watch
no,
any movie, read any book?
no,
Exactly. No. So when we are transmitting a signal, when we are modulating a signal, our purpose is to convey information. And information arises out of randomness.
Sir, but uh, you were talking about carrier signals, right? We don't
No, no,
want,
no,
I
no,
mean,
no, 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 no. I was talking about modulating,
oh, okay.
modulating using deterministic signals.
So, okay, okay, sir.
sir. Do
Okay.
you mean that the when we are speaking of deterministic signals, it is deterministic with respect to the receiver or with respect to the?
Deterministic with respect to the receiver.
Then obviously we are not interested with deterministic signals.
Yes. Yes, yes, yes. So deterministic, I meant deterministic with respect to the receiver. Even deterministic with respect to the so everything that the transmitter is transmitting. So I know what I'm going to say next. You do not know what I'm going to say next. Or rather, when they sent out the movie details of Avengers Endgame, the guy who was playing the movie, he knew that Tony Stark is going to snap Thanos out of existence. You didn't know that. You watched the movie because of that. So randomness is always with respect to the receiver. I won't be sure of that. So, or rather, ah, so in that case, yeah, I didn't know that there were 4 or 5 copies. But so I would say that what? Anyway, my point is that that randomness is always with respect to the receiver and not with respect to the transmitter. So any guy who is creating randomness, or that is a special case that you are, that's a form of encryption. And the player in that case, or cinema, the guy who plays the movie is more like an eavesdropper. We will come to that if we ever have a course on or communication security. But that's an eavesdropper problem in general. You are, when I said this, I was treating that fellow as a transmitter, but in your model, that fellow is an eavesdropper. So yeah. So the point still is that we want to transmit random signals, or we want to receive random signals. So, but till now, unless till we study random signals in detail, we'll confine ourselves to deterministic signals, and we'll see that even random signals can be characterized in terms of their Fourier transforms. So that's why we are interested in analyzing the spectrum of an FM signal. We had seen that an FM signal.
Sir.
Yeah, Shubhashish.
When you mention m of t or x of t, is it deterministic or is it random?
Right now, these are until we reach random processes, these are deterministic.
Okay.
Okay. So now, so I'll repeat what we did yesterday. Now, for a deterministic MT equals AM cos 2 pi FMT. For this thing, seen that ST equals AC cos 2 pi FCT plus beta sine 2 pi FMT, where beta is KF AM over FM. We discussed this yesterday, and I can alternatively write ST equals the real part of AC e to the power j 2 pi FCT plus beta sine 2 pi FMT, right? S tilde T, which is the low pass equivalent of this ST, is AC e to the power j beta sine 2 pi ST equals you can see this for yourself, that ST will be equal to ST plus ST plus K over FM. So, therefore, ST periodic
Sir, is it ST or S tilde T?
sorry, S tilde T. Thank you. I was trying to do something else. Yeah. So yeah, S tilde T is periodic with period 1 over FM. Let's call this period Tm equals 1 over FM. Fine. And based on this S tilde T, as a summation k goes from minus infinity to infinity, S tilde k e to the power j 2 pi k right, S tilde k e to the power j 2 pi k fmt, and equal to FM AC minus 1 over 2 FM to 1 over 2 FM e to the power minus j 2 pi k FM t minus beta sine 2 pi FM t dt. This beast. Fine.
Sir, why is in minus?
Sorry.
We
Now is it okay?
uh,
Sorry, that Fourier series expression I had written slightly incorrectly, so I make this mistake a lot. Yeah. So this is dt, not df. This looks my t looks like f. So one good thing about these online classes is that I have finally realized after being told for around 30 years how bad my handwriting is. They've been telling me since I started school. And now I realize that, okay, even I cannot read my own handwriting properly. Yes. So this, and now what do we do with this? For this, let x equals 2 pi fmt. Therefore, dx, or rather fm dt, equals dx by 2 pi lower limit minus 1 over 2 fm equals minus pi, and 1 over 2 fm equals pi. Fine. And s tilde k equals ac over 2 pi minus pi to pi e to the power j beta sin x minus kx fine. You all of you just take a minute to absorb this. So I've just changed the variable in integration. This is fine.
Yes, sir.
Yeah, excellent. So since this is fine, now we have to minus pi to pi x. So any ideas on how to deal with this beast?
So can't we force beta to be at extremes?
Okay, so you haven't done so in your mathematics. You have had 2 courses of mathematics or three?
3.
Three. Okay. So did you have a so we used to have a short chapter that was completely useless actually, but still used to have a chapter on special functions. Have you had that? Special integrals, special functions? No, it seems you haven't. Okay. So this is a so this thing, or rather jk of beta equals 1 over 2 pi minus pi to pi e to the power j beta this this goes here j beta sin x minus kx dx. This is a special integral and cannot evaluated in a closed form. So you all of you know that there are certain special integrals that cannot be evaluated in a closed form. You have encountered those, right? So you have seen these integrals, these kind of integrals. No, you haven't. So you class 12th, did you did no one try to evaluate that expression called that e to the power x square integral? E to the power x squared dx. There are a lot of yeah. So the thing is that yeah. So e to the minus x square or e to the power x square. I don't remember that. So these kind of integrals, the thing is that whatever tricks that we use for integration, these things cannot be solved in a closed form. So you have to have this. So we saw that, or it is seen that these integrals, this integral actually in closed form, and this integral is actually a solution of the differential equation. Integral is the solution of the differential equation given as beta square plus y is a function of beta. So this is a so this equation has since this is a second order linear differential equation, there are two solutions. So based on this, we call, so the solutions of this equation are called the Bessel's function. So since there are two forms of the solution, these are called the solutions to this solutions to this called Bessel functions of the first kind or the second kind. We will be interested in the first kind. The first kind solution equals this. So jk beta has this form, and it can be reduced to series.
Sir,
Yeah, Shubhashish.
can't we use the Newton's method to approximate the solution?
You can, but so Newton's method. Wait a minute. Newton's method is for uh, what do you call it? Newton's. You are talking about the Newton-Raphson method, right?
Yeah.
So the Newton-Raphson method is for polynomials. One. Newton's method is for polynomials. For differential equations, so for integrals you have the Simpson's rule, and for differential equations you have the Runge-Kutta method. Newton's method is for polynomials. This is not a. This is most definitely not a polynomial. Polynomial, or even for polynomial-like functions like transcendental equations, you can solve using uh, this, but not differential or integral equations. So this can be used to reduce to a series summation. So thankfully for us, this can be reduced to a series summation, and you can sum this series to get here. So, and MATLAB has MATLAB, NumPy, both of these have inbuilt functions to sum this series. So we don't need to bother much as well. So JK beta can be written as a series with summation m going from 0 to infinity minus 1 to the power m divided by m factorial into k plus m factorial. It's not k minus m, it's k plus m factorial to k plus m factorial beta by 2 2m plus k. So if you sum this weird series, you have a chance of solving or you have a chance of evaluating the Bessel function. And so therefore S tilde k equals AC jk of beta and S tilde t equals AC summation k goes from minus infinity to infinity jk beta e to the power j 2 pi k fmt. So what this whole exercise tells us, can anyone summarize all our mathematical jugglery for me? Yeah, it's maths, but yeah, I agree that it's maths, but can you summarize that? Summarize what we have done? That would be my question. I agree that this is all mathematical jugglery. That's what that's the word I would like to use. But can you find a message behind this?
Sir, our coefficients are basically answers to the differential equation.
Our coefficients are Bessel functions. So, or rather, I would state it like this. When we modulate, when we frequency modulate, This is important when we frequency modulate a sinusoidal carrier with, or rather I would do one more thing first and then I'll jump to this. So I'll come to this, but let's do something else first. Therefore, since st equals real part of s tilde t j 2 pi ct, since st equals this, st equals, sorry, st equals ac real part of ac jk beta e to the power j 2 pi k fmt plus fc plus j 2 pi fct, right? This can be written as ac cos, or
So what about the summation?
yes, there is a summation k equal to minus infinity to infinity. AC outside, summation k goes from minus infinity to infinity, jk beta cos 2 pi kfm plus fc t, right? We see this beast. Sorry about the summation in the previous step, but we'll see this beast now. So this is a periodic signal, isn't it? So this is also. Now let's have add a physical meaning to this. So when we frequency modulate a sinusoidal carrier with another sinusoidal function, we get a periodic signal with, I would say, or comprising from the frequencies from the set fc minus kfm, and k is an integer for all k in z, such that the contribution of the sinusoid with frequency fc minus kfm to the overall signal is jk. Fine. So this is a way of interpreting this thing. And based on this, we can write summation k goes from minus infinity to infinity jk beta delta f minus fc minus kfm plus delta f plus fc plus. This is what things will look like in the frequency domain. So in short,
So,
yeah, Shubhashi, just a second, let me finish this sentence. In short, the behavior of the spectrum of an FM signal, even in this simple case, depends on the of jk beta. Yeah, now
so isn't it then bad because our spectrum is basically lying over a larger region?
so uh, we haven't yet talked about noise. Okay, so yes, I agree that the spectrum is, if you look at it, actually the spectrum is not even not over a larger region. The spectrum is infinite.
Yes.
So each FM signal is actually using infinite bandwidth, right?
Yeah.
But thankfully, you have multiple FM channels coming to your house, or your car radio, your cell phone can receive signals from multiple FM channels, or can receive multiple FM channels, right?
So, but it doesn't make sense because
It
we
will make
have.
sense. It will make sense. Just give it another, or give me another 1 hour. So we'll actually stop here today, because I feel that today the lecture has been mathematically too heavy. So you would need some time to digest this before we proceed further. And before I start discussing about this Bessel's function. So the Bessel function is important. We need to we need to discuss its properties in order to evaluate this signal better. So we'll continue from this point tomorrow. If you have any doubts till now, you can ask.
Sir, our jk of beta is a single value, right?
Jk of beta is a single value. Jk of beta for each k and beta will have a unique value.
Okay.
Okay, so we'll stop here and continue tomorrow. Those interested and those awake can look at the Wikipedia description of Bessel functions. It's informative. Okay, then I'll disengage and start tomorrow. Bye.